Hi, today we're going to go over the Machine Learning Coursera course, Practice Lab Decision Trees. We're going to implement a decision tree from scratch and apply it to classifying whether a mushroom is edible or poisonous. Packages, NumPy, matplotlib, and some helper functions. So we are starting a company that grows and sells wild mushrooms, but we don't want to poison our customers because poisoning our customers is probably not good for business. So we want to identify if our mushrooms are edible or poisonous. Now, how do we do this? It's because when we see the mushrooms, we can see that they have different physical characteristics, such as different cap colors like red or brown, different stalk shapes, and is it solitary, which mean like is it by itself or is it with a lot of its friends, and whether or not, and this tells us whether or not it's edible. So we have one hot encoded our data set. So one hot encoding means we turn our features into 0 or 1 values. So in this example, it has a brown cap, it does not have a tapering stalk shape, it is not solitary, and it is therefore not edible. And we're going to see our data over here. So X-train and Y-train are these values from our NumPy array. So the first few elements of X-train look like this, and Y-train looks like that. And the dimensions, there are 10 examples. Decision tree refresher, I'll let you pause this to read it if you want. Calculate entropy. We're going to compute a function called compute entropy, which computes the entropy at a node. And we have a NumPy array Y, which tells us if the examples are a 1 or a 0. And we're using this formula over here, which has P1 in it, which is a fraction of examples that are edible. And we have some notes over here. Okay, let's do it. So if length of Y is not equal to 0, so meaning if the array is not 0, we're going to calculate the fraction, which is so all the array examples which have 1 in it will be divided by the total length of Y. And because 0 log 0 is 0, if P1 is 0 or P1 is 1, we set the entropy to 0 dot because it's a float. Else, we can now compute the entropy with this formula over here. And we run it, and all tests passed. Split dataset. We're going to write a different helper function called split dataset, which splits the data into the left and right branches for a particular feature. So in this example, we are starting at the root node, and we're splitting on whether or not it has a brown cap. And so in the end, we're returning this array, left indices, which are the mushrooms that have a brown cap. And these are the ones that do not have a brown cap. Split dataset. We have X, an array, and node indices, and the feature. And we want to return left indices and right indices. So for each index in node indices, if the value of X at that index for that feature, so that's fx bracket I bracket feature, if that is equivalent to 1, we are adding the index to the left indices. So left indices dot append the index, and else we append it to the right index. and this visualizes it with a graph. So this is what we returned, the left indices and right indices, and this graph shows us that these mushrooms are the brown cap ones and these are the ones that don't have a brown cap. Same with this one. Now we're going to calculate information gain for a particular node using this formula over here. So we have x, y, node indices, and feature, and we're returning cost. So we are using the formula we just wrote above, split the data set, so we have the left indices and right indices. We have some useful variables. So we're starting at y node, and we're going to compute the entropy at the y node first. So we're using the formula we wrote above to find the entropy at y node. Then we have left and right nodes, because in this formula we have the entropy at the node minus the proportion of examples at the left branch, so this fraction of examples that are on the left side of the tree, times the entropy at the left tree plus the same for the right. So we need all these individual formulas, all these individual variables. So we're first calculating the entropy for the y node, which is the node's entropy. And we can also get the left entropy. At the left node, which is y left. And the right entropy, which is y right. To get this y left variable, it is the fraction of x left divided by length of x node. So this will give us the fraction like 3 out of 10 we have 3 out of 10 examples on the left side of the tree, and maybe we have 7 examples on the right side of the tree. And the weighted entropy, which is this part of the formula, is W left times entropy left. So W left times left entropy plus W right times right entropy. And the information gain will be the node's entropy minus the weighted entropy. And syntax error at line 39, which I'm not sure where that is. Let's see. Right here, entropy, oh. And all tests passed. So based on this, we can find out that solitary has the best feature to split on at the root node, because the information gain, or the amount of information you can gain from knowing about this solitary, whether or not the mushroom is solitary or not, is greater than tapering stalk shape and brown cap, because 0.27 is bigger than these numbers. Get best split. We're writing a function to get the best feature to split on by computing the information gain from each feature and returning the feature that gives the maximum information gain. So we have x, y node indices, and we're returning best feature, which is the index of the best feature to split on. And we have known features, which has our information gain from the features, and we're returning this best feature thing. Okay, so we're going to have a variable called max info gain set to 0, and we're going to be comparing the information gain from each feature. So for each feature in range of known features, we can find the information gain from this feature with this compute information gain function. And it's going to take in x, y node indices and feature. Now if info gain is greater than max info gain, we're going to set max info gain to be equal to the info gain, the updated info gain. And therefore the best feature will be this particular feature that we're on. And we're going to keep iterating and iterating through, and this will find out the feature with the highest information gain, and all tests passed. And we found out that the best feature to split on at the root node is solitary. Now we're going to use all the features, all the functions we implemented to generate a decision tree by successively picking the best feature to split on until we reach the stopping criteria, which is max depth is 2. And this will build the tree recursively, and this code is for the visualization. And it will find out that this is the best tree, and we split and split and split based on these features. Thanks for watching.